Stacey Jeffery, who's going to be speaking about quantum homomorphic encryption for circuits of low T-gate complexity.
Thank you, and thanks everyone for sticking around for my talk, which I realize is the last talk before the free afternoon, so I definitely appreciate you being here. I'm going to be talking about quantum homomorphic encryption, which is the quantum version of a very important result from about 6 years ago in classical cryptography. We make partial progress towards this result, giving quantum homomorphic encryption schemes for circuits of low T-gate complexity. And this is joint work with Broadbent. Classical homomorphic encryption was proposed in 1978 by Rivest, Adelman, and Dertouzos. And it's a cryptographic primitive which when it was first proposed, it wasn't even clear if it was possible because it asks for something that seems like it would be very difficult to achieve. We want some way of encrypting a classical message x so that some other party can evaluate a function f on x without being able to decrypt x. So given an encryption of x, someone should be able to turn that into an encryption of f of x without actually being able to learn anything about the message x. And this was a very difficult problem, which was open for over 30 years, until 2009, when Craig Gentry gave the first classical fully homomorphic encryption scheme. So this was a scheme where one could encrypt any classical message, and then any function could be evaluated on the encrypted message. Since then, there have been a number of other fully homomorphic encryption schemes. And this is a very important result in classical cryptography. But we know that actually this isn't really fully homomorphic encryption because there's a lot more that you can do to information than just applying some kind of classical function. There's a lot more information than just classical information. So I'm going to be talking about the quantum version of this called quantum homomorphic encryption. And this generalizes the idea of classical homomorphic encryption in two ways. So first, we would like to be able to encrypt any quantum state, not just a classical message. So we want an encryption scheme that encrypts, that hides any quantum state. And furthermore, we want to be able to homomorphically evaluate any quantum circuit C on the encrypted state. So if we give someone an encryption of this quantum state rho, they should be able to turn it into an encryption of the state you would get if you applied the quantum circuit C to rho. So just as an example, suppose I wanted to encrypt some integer, which of course is classical, and give it to someone and have them homomorphically factor it for me. This would already have been possible using classical fully homomorphic encryption. Someone could just, use some classical circuit for factoring and homomorphically factor my integer. So I could use, for instance, Gentry's original scheme or one of the more modern ones. However, this would necessarily take super polynomial time as long as we don't think that there's a polynomial-sized circuit for classically factoring. Whereas if we had a quantum version of fully homomorphic encryption, then we would be able to have someone homomorphically apply a quantum circuit for factoring, which could be done in polynomial time. So this would be one way of getting quantum speedups homomorphically. And so in my talk today, we don't achieve this full functionality, but we make partial progress towards quantum fully homomorphic encryption. So to begin, let me define more precisely what I mean by homomorphic encryption. And I'm going to start with classical homomorphic encryption, which is very similar to quantum homomorphic encryption. So a classical homomorphic encryption scheme consists of 4 polynomial time randomized algorithms. The first is some key generation procedure, which takes some security parameter, kappa, and it outputs 3 keys. So there's a decryption key, sk, an evaluation key, evk, and an encryption key, pk. And then there's an encryption procedure, which takes the encryption key and some message m and outputs a ciphertext. There's an evaluation procedure, which takes a ciphertext and an evaluation key, and also some classical function f, which should be given as a circuit, so some list of gates over some universal classical gate set. And then the evaluation procedure outputs some other ciphertext. And then there's a decryption procedure, which takes a decryption key, a ciphertext, and outputs another message, which is hopefully the result of applying the function f to the message m. So in the public key setting, we can imagine that Alice might generate some keys and then make her evaluation key and encryption key public. And then Bob could use Alice's encryption key to encrypt a message m of his choice. And then he could give the resulting ciphertext to Charlie. And then Charlie could choose some function f, express it as a classical circuit, and then use Alice's evaluation key, run the evaluation procedure, and output another ciphertext C prime. And then when Alice decrypts C prime using her decryption key, she should get f of m. So the only difference between like a regular public key encryption scheme and this homomorphic setting is the existence of the evaluation procedure in between encryption and decryption. Okay, and then we could also consider the private key setting in which Alice does not reveal her encryption key. And in this case, Alice would generate keys, encrypt a message, and then Charlie could evaluate a function on Alice's message, which she could then decrypt to get f of m. But for simplicity, we'll just be sort of imagining things in the public key setting. So we would like such a scheme to have certain properties. Of course, we would like it to actually be correct in some sense. So we say that a scheme is C homomorphic, where C is some class of circuits. If for every f in C, this actually works. So that means that for any message m and any f in C, if Bob encrypts m and then Charlie homomorphically evaluates f and Alice decrypts, she will actually get f of m, at least with high probability. Okay, and of course, this is an encryption scheme, so we would like it to be secure. So in some sense, we require that the encryption of a message m using a public key PK should hide m. And the standard sense of security that is generally used is the notion of indistinguishability under chosen plaintext attack. And on a high level, this just says that no polynomial time adversary should be able to distinguish an encryption of 0 from an encryption of 1 with non-negligible success probability. Okay, and then finally, there's one other property that we're going to require. So to motivate the third property that we want, I'm now going to explain how we could trivially construct a scheme that has both of these properties. So this scheme is called the trivial scheme, and it's going to be homomorphic for all circuits, and it's going to be secure. And we're just going to start with like a regular standard public key encryption scheme. So that has a key generation procedure, an encryption procedure, and a decryption procedure, but it does not have any kind of evaluation procedure. And from this, we're going to construct a scheme that is homomorphic for any classical function. So the key generation procedure in our new scheme, triv.keygen, it's just going to call the public key generation procedure, which outputs an encryption key and a decryption key, not an evaluation key, but we're not going to use an evaluation key here. And then to encrypt a message, we're just going to encrypt a message using the public key scheme that we started with. Okay, now we need an evaluation procedure, and our public key scheme does not have an evaluation procedure. So our evaluation procedure is just going to be, we're going to take a ciphertext C and some circuit F, and we're just going to concatenate them. That's how we're going to evaluate F on C, is we're just going to take C and concatenate it with our description of the function F. And then to decrypt, we're just going to decrypt C to get M, and then apply F to get F of M. So this is clearly homomorphic for every function F. And it is also secure as long as we started off with a secure encryption scheme. But this is obviously not at all what we wanted, because we've somehow cheated by pushing all of the work of evaluation into the decryption procedure. So we actually want that evaluation really happens during the evaluation procedure, and it doesn't just happen after you decrypt. And so we require a third property called compactness. We say that a scheme is compact if the complexity of decryption does not depend on the evaluated function f. So we actually require that evaluating really happened at the time of the evaluation procedure and is not just pushed until the decryption phase. Okay, so now I can actually define a quantum homomorphic encryption scheme, but it's very similar. It now consists of 4 polynomial time quantum algorithms. So again, we have a key generation procedure. And in our schemes, we always have classical decryption and encryption keys, SK and PK. But in some of our schemes, we have a quantum evaluation key. But we could also have used quantum encryption and decryption keys. Then we have an encryption procedure. It takes some quantum state row on a system M, and it outputs another quantum state on a system C. The evaluation procedure now evaluates on a quantum ciphertext. And it's going to now take a classical description of a quantum circuit, C. So C is going to be some quantum circuit over some universal quantum gate set. But we can, of course, describe this as a classical string. And then we want that when Alice decrypts the output of eval, what she gets is the quantum state resulting from applying the quantum circuit C to the original quantum message row M. And again, we require essentially the same properties. We say that a scheme is Q homomorphic, where Q is a set of quantum circuits now, if this actually works for all circuits C in Q. And we also have a definition of quantum indistinguishability under chosen plaintext attack. So this is like a quantum version of the classical standard security definition. And on a high level, this just says that no polynomial time adversary can distinguish an encryption of rho, some state chosen by the adversary, from an encryption of a maximally mixed state. And then we also require compactness. So the complexity of decryption should not depend on the complexity of the evaluated quantum circuit C. So since one of the main differences between classical homomorphic encryption and quantum homomorphic encryption is the difference between classical and quantum circuits, let's compare classical and quantum circuits. In the classical case, addition and multiplication form a universal gate set, although we would have had other choices. Every classical fully homomorphic encryption scheme is over these gate sets. And if you want to homomorphically evaluate a classical circuit, you would want to consider maybe evaluating it gate by gate. So it would be enough to just be able to homomorphically add 2 ciphertexts and homomorphically multiply 2 ciphertexts. And addition is kind of the easy operation here. So there were some, before classical fully homomorphic encryption, there were some results that allowed you to homomorphically evaluate circuits in many additions but very few multiplications, or for instance, low multiplicative depth. And even in the fully homomorphic encryption schemes that exist today, addition is always very easy. It's just, you just take 2 ciphertexts and you add them, and that results in adding the messages. Whereas multiplication is like a more involved procedure that you have to do to actually have homomorphic multiplication of your messages. So on the classical side, addition is sort of the easy thing to do homomorphically, whereas multiplication is kind of the bottleneck to getting fully homomorphic encryption. So on the quantum side, we have a lot of choices for our universal gate set, but we go with some pretty standard ones. So we start with the Clifford generators. So we have H, a Hadamard gate, and P, a phase gate, and then a control not gate. So these generate Clifford circuits. And these contain all of the classical circuits generated by reversible addition, which is just control not. But they're also more powerful than classical circuits. They do contain actual quantum gates. However, they're not or I guess I shouldn't say they're more powerful, they're really incomparable with classical circuits. So they contain non-quantum gates, but Clifford circuits cannot perform, for example, a multiplication. And then to get a universal quantum gate set, it suffices to add any non-Clifford gate, and we go with the standard T gate, but we could have chosen any non-Clifford gate to add to the Clifford generators to get a universal quantum gate set. So for instance, we could have chosen, instead of a T gate, a Toffoli gate, which is reversible multiplication. So we should really think of a T gate as being kind of the analog of multiplication in our gate set. And as we'll see, it is also going to be the bottleneck to quantum homomorphic encryption. It's going to be our hard gate. Okay, so now let me get to our results. So first, I'll talk about some prior related work. There's been a number of papers on secure delegated quantum computing, and a lot of our techniques actually come from this literature. And I want to explain a bit how this setting is different from quantum homomorphic encryption. So in secure delegated quantum computing, some client, Alice, wants Bob to perform a quantum computation for her. She has perhaps not very much quantum power herself, but she doesn't want Bob to know, what the input to her computation is. So she sends Bob some encrypted input, and he performs. Or sorry, this is in homomorphic encryption. So in the setting of homomorphic encryption, Bob performs the computation and then sends Alice a message back, and there's no interaction between the two of them. So Alice just sends Bob an encrypted message. He homomorphically does some computation and then sends something back to Alice. But in the setting of secure delegated computation, in contrast, while Bob is performing his quantum computation, he has constant interaction with Alice. So that's one of the major differences here between our setting and secure delegated quantum computing, is that we don't allow interaction between Alice and Bob, aside from initially when she sends her input and when Bob returns the output. And another thing that I'll mention is, although homomorphic encryption has a lot of potential for delegated computation, it's not built into the definition that Alice, the encryptor, has less quantum power than Bob. So it would, of course, be really nice if a classical Alice could encrypt a message and have Bob do some quantum computations and give her back some classical message, but that's not actually required in the definition of quantum homomorphic encryption. Okay, and some other work that came out a bit before ours. One result showed that quantum fully homomorphic encryption is not possible with information theoretic security. So, of course, sometimes we can do things quantumly with information theoretic security that would not be possible classically, but it turns out that this is not one of them. So this kind of justifies us considering computational assumptions. And then some other work previous to ours did look at quantum homomorphic encryption with information leakage, but this does not give any kind of semantic or cryptographic security, so this work is incomparable with the results that I'm presenting now. Okay, so now I'll get to our results. Let me first mention, we have quantum fully homomorphic encryption would be homomorphic for all quantum circuits. It would be compact, and it would be have some kind of security, like quantum indistinguishability under chosen plaintext attack. What could we do in this framework trivially? So by not encrypting, we get a scheme which is homomorphic for all quantum circuits. You can just do a computation on it because it's not encrypted at all, and it's of course compact, and it's and it has no security at all because you didn't actually encrypt anything. So this is one of the trivial things we can do. And as I mentioned before, the trivial scheme that I showed you, this is homomorphic for all quantum circuits, and it is secure, but it's not compact. So the complexity of decryption scales with the number of gates in the evaluated circuit. And another thing that we can do trivially is some kind of quantum encryption, like the quantum one-time pad. This would not be homomorphic at all, but this would be compact and secure. So getting any two of the three properties is easy, but getting all three properties at once is the real challenge. So our results are sort of intermediate between these trivial results and our ultimate goal of quantum fully homomorphic encryption. So we have three schemes. The first is homomorphic for all Clifford circuits. So we call this scheme CL, and it's compact and Q and CPA secure. And this scheme is quite straightforward, and I'll actually be going through it in the rest of my talk. And then our second and third schemes are both extensions of the first scheme. So the second scheme extends the first scheme to quantum circuits that are arbitrary in Clifford gates but have only constant depth in T gates. And this scheme is also compact and Q and CPA secure. And then our third scheme builds on our first scheme in a different direction. So it's homomorphic for all quantum circuits, but it's not compact. So the complexity of decryption scales like the number of T gates squared. So this is an improvement over the trivial scheme as long as there aren't too many T-gates. In particular, this only depends on the number of T-gates in the circuit. And this scheme is also QNCPA secure. OK, so now let me talk about our first scheme, the Clifford scheme. So let's first review the Pauli group. We have these important Pauli gates, the X gate, which is just a classical NOT gate, and the Z gate, which is just like a NOT gate in the Hadamard basis. And we're going to use this notation. If A is some n-bit string, x to the A will just refer to the n-fold tensor product of x to the A1 up to x to the AN. And then the Pauli group, Pn, is just x to the A, the group of x to the A, z to the B for all n-bit strings A and B, up to some phases that are not relevant for our purposes. And it turns out that applying a random Pauli is an information theoretically secure way of encrypting a quantum state known as the quantum one-time pad. OK, and then the Clifford group is just the normalizer of the Pauli group. So what this means is that for any Clifford C and any Pauli x to the A, z to the B, if you conjugate the Pauli by the Clifford, you get another Pauli. Or in other words, you can see this in terms of circuits. Applying some Pauli followed by a Clifford C is equivalent to applying C followed by some other Pauli. And what is this other Pauli? It depends on the circuit C and the original Pauli. So there's some function that depends on C, so f sub C, which maps A and B to A prime and B prime such that this identity holds, such that it is always true that C times x to the A, z to the B is equal up to some phase to x to the A prime, z to the B prime times C. And it's not obvious, but the circuit f sub C is always linear for, or this function is always linear for any Clifford C. So for example, one example of a Clifford is this phase gate P, which satisfies this identity. So we could say that f sub P of AB is equal to A plus B mod 2. OK, so now I can present our scheme. So we already have the first two ingredients, the quantum one-time pad and just the definition of the Clifford group. And the final thing we're going to need is some classical homomorphic encryption scheme, which just consists of classical key generation, encryption, evaluation, and decryption procedures. And now we can construct our quantum scheme, which is homomorphic for Clifford circuits. OK, so our key generation procedure, cl.keygen, is just going to call the classical key generation procedure and output the 3 classical keys that it generates. And now to encrypt a quantum state, what we're going to do is we're going to choose random A and B, and then encrypt the quantum state using the quantum one-time pad. So we're going to encrypt it using x to the A, z to the B. And then we're going to output the quantum one-time pad encrypted state, as well as classical encryptions of the quantum one-time pad keys A and B. OK, so A tilde and B tilde are just classical encryptions of the quantum one-time pad keys A and B. OK, now to homomorphically evaluate any Clifford circuit, we're going to apply the Clifford circuit C to the quantum one-time pad encrypted state. And then because of number 2 up here, that's going to result in us having a quantum one-time pad encryption with keys A prime and B prime of the state C applied to psi. And then finally, we're going to homomorphically evaluate the function f sub C on our encryptions of A and B to get encryptions of the correct A prime and B prime. So now to decrypt, we're just going to decrypt our encryptions of A prime and B prime, and then we have keys A prime and B prime, which we can use to undo the quantum one-time pad. And the result is just the Clifford circuit C applied to our original state psi. OK, so it's not difficult to convince yourself that this encryption scheme is as secure as whatever classical scheme we started with. So, and this is clearly homomorphic for any Clifford circuit because of the, just because of the the definition of Clifford's. Another thing I'll point out is that we don't even need a classical fully homomorphic encryption scheme. We just require a scheme that is homomorphic for